High pressure processing food irradiation, ultrasound.
In this module, we'll discuss about various minimal thermal processing of food, that is high pressure processing, food irradiation and application of ultrasound in food. Coming to the high pressure processing, as the term says, high pressure means food under high pressure. Coming to an example, suppose I will say a grape. If I will press the grape by my two hands, then it may burst. The bursting is due to pressure. But if pressure is equally applied from all sides, then there will be no bursting. Coming to the food irradiation, how the irradiation can be applied in food, we will study in more details. Ultrasounds are the sound with high frequency, that is above 20 kHz, which cannot be detected by human ear. So we will discuss about the application of three processes in food processing.
Let us first discuss on high pressure processing.
High pressure processing, HPP, is a method of food processing where food is subjected to elevated pressure, 6,000 atmospheres approximately. It also called as high hydrostatic pressure. High pressure processing is applied to achieve microbial inactivation or alter the food attributes in order to achieve consumer desired qualities. HPP retains food quality, maintains natural freshness, and extends the microbiological shelf life. The pressure requirement for inactivation of fungi, virus, vegetative bacteria, and for spores.
Now coming to principle. What is the main principle involved in this process? The product is packaged in flexible container, pouch or plastic bottle and is loaded into a high pressure chamber filled with a pressure transmitted hydraulic fluid. Water, castor oil, silicone oil, sodium benzoate, ethanol and glycol are used as pressure transmitting hydraulic fluid. The hydraulic fluid, that is water, in the chamber is pressurized with a pump, and this pressure is transmitted through the package into food itself. Pressure is applied for a period of 3 to 5 minutes. Processed product is removed and stored in conventional manner. Pressure uniformly transmitted. Food maintained shape, sensory characteristics without compromising microbial safety.
We are applying the force on the food product in a container. During HPP, pressure is uniformly applied around and throughout the food product. For example, an orange placed between palms can be easily squeezed. This is because the pressure is not applied evenly from all sides simultaneously. On the other hand, if the same orange is squeezed from all sides simultaneously, it will not be crushed. This can be demonstrated by placing a pre-packed food inside a bottle filled with water. By squeezing the bottle, we pressurize the water inside as well as the pre-packed food. Yet the food is not damaged no matter how much pressure is applied. In the same way, foods processed by high pressure will not be damaged by the applied pressure.
What is the scientific principle involving in HP processing? Le Chatelier's principle. Chemical reactions which result in a decrease in total volume are enhanced by pressure. Conversely, reactions resulting in an increased total volume are slowed down by pressure. Decrease in total volume, negative activation volume. Increase in total volume, that is positive activation volume. Isostatic rule. The high pressure process is volume independent. Therefore, pressure is instantaneous and uniform throughout the pressure vessel.
By using high pressure, we can kill the microorganisms by inactivating its activity. Number 1. This process mainly concentrates the reduction of the activity of pathogens. Number 2, it will totally reduce the microbes and it will also cause sublethal injury to pathogens. The different microorganisms are bacteria, bacterial spores, fungi, yeast, molds, viruses, prions. These microorganisms react to HP treatment with different degrees of resistance.
What are the factors influencing microbial sensitivity to high pressure? pH. Compression of foods during HP treatment may shift the pH of the food as a function of applied pressure. The direction of pH shift and its magnitude must be determined for each food treatment process. Water activity, that is AW. Reducing the AW appears to protect microbes against inactivation by HPP. Temperature, pressure and holding time. Increasing treatment pressure, holding time or temperature will generally increase the number of microorganisms inactivated while many HP processes are performed at ambient temperature. Temperature above 45 to 50 Celsius increase the rate of inactivation of food pathogens and spoilage microbes. Temperature increases due to adiabatic compressions can be 3 Celsius or more per 100 MPa.
What is the effect of high pressure on food quality? HP processing offers the food industry a technology that can achieve the food safety properties of heat-treated foods while meeting consumer demand for fresher tasting foods. The different effects involve effects of high pressure on food color, effect of high pressure on food texture, effect of high pressure on food sensory quality, effect of high pressure on food yield, effect of high pressure on enzyme activity.
Benefits of high pressure processing. The product can be processed chilled or at a room temperature, so sensory properties and nutrition are not affected. Chemical bonds in the foods are not affected and so cause little change to the natural properties of the food. The process will destroy food-borne pathogens and organisms such as yeast and molds, so food will maintain a longer shelf life. Food sensitive to heat can be pasteurized. Pressure is applied evenly, so food retains its shape and the texture is not affected. Chemical preservatives are not required.
Concerns about high pressure processing. HPP cannot be used to process foods low in acids such as milk, vegetables or soups, as this process does not destroy the spores without the addition of heat. All products that are not acidic require refrigeration. The establishment cost for setting up high pressure processing is high. It is used for high value foods, so they may be expensive for consumers to purchase. Only a limited range of foods is processed using high pressure processing.
Some more concerns about high pressure processing are: must not have any internal pockets of air, as they can crash under high pressure, that is solid foods with air included cannot be HHP treated. For example, bread, marshmallows. Packaged food in completely rigid packaging cannot be HHP treated. For example, in glass, canned. Food with a very low water content cannot be HHP treated, hence food must contain water to ensure all bacteria that cause food spoilage and foodborne diseases are destroyed. For example, spices, dry fruits.
Now let us discuss about another non-thermal processing technology, food irradiation.
What is radiation? Radiation is basically energy moving through space in invisible waves. The nature of the energy is defined by the wavelength of the energy. As the wavelength gets shorter, the energy of the wave increases. Type of radiation. Ionizing radiation. Radiation that has the ability to produce ions, electrically charged particles. For example, alpha particle, beta particle, high energy electron, gamma ray, and X ray. Non-ionizing radiation does not have sufficient energy to create ions, instead tends to excite molecules without removing electrons. For example, visible light, television wave, radio wave, and microwaves.
Let us discuss about food irradiation. What is food irradiation? Irradiation is a process in which food is exposed to a low level of ionizing radiation to kill bacteria, molds, yeast, parasites, and other microorganisms that can lead to food spoilage and illness if untreated. This process helps to control foodborne pathogens, reduce microbial load and insect infestation in habit and germination of root crops, and extend the durable life of perishable produce. Principles of food irradiation. Radiation is absorbed by the food and more particularly by the microbial organisms in the food. This absorption disrupts the complex organic molecules of the microbes, either preventing the microbes from reproducing or killing them.
Now coming to production of irradiation, it is mainly of three types: gamma ray irradiation, E-beam irradiation, and X-ray irradiation. First, gamma ray irradiation. Gamma rays are produced from the radioactive decay of cobalt-60 2.5 MeV and cesium-137 0.51 MeV. MeV is equal to million electron volt. Idealized penetration in a homogeneous food matrix of 1 gram per centimeter cube is 30 to 40 centimeter. This radiation is suitable for all products. Gamma radiation has higher penetration depth than UV and X-ray photons. Second, E-beam irradiation. Source of electron beam is accelerated electrons, typically 5 to 10 MeV. It has short penetration depth. Idealized penetration in a homogeneous food matrix of 1 gram per centimeter cube is 6 to 8 centimeter, and this radiation is suitable for relatively thin or low density products. Third, that is X-ray irradiation. X-ray is induced by impingement of electron beam onto a metal plate. Idealized penetration in a homogeneous food matrix of 1 gram per centimeter cube is 30 to 40 centimeter and is suitable for all products.
Now let us discuss about the unit for measurements of radiation. 1 gray is the absorption of 1 joule of radiation energy by 1 kilogram of matter. 1 gray equals to 1 joule per kg. Gray equals to 100 reds. Red represents the radiation absorbed dose and is the older unit. Kilogray equals to 1000 gray. Levels of food irradiation. Radioization less than 1 kilogray. Vegetable sprouting, fruit ripening, insect sterilization. Radicidation 1 to 10 kilogray. Kill most pathogens and many food spoilage organisms, kills insects and parasites. Rapidization greater than 10 kilogray. Can sterilize by killing all bacteria and viruses.
Let us discuss about the application part. First, reduction of pathogenic microorganisms. Importance for the control of foodborne illnesses in seafood, fresh produces, and frozen meat products. Reduce the number of disease-causing bacteria such as Listeria monocytogenes, Salmonella, Clostridium botulinum, etc. in food commodities. Second, decontamination. After 10 kgy irradiation, The total count of aerobic and anaerobic bacteria and molds decreased and the antibiotic value in honeys increased. Used as a method for decontaminating medicinal herbs, and a dose of 10 kgY can obtain a satisfactory result which does not affect any pharmacological activity.
Extension of shelf life. The shelf life of many food increases by treatment with irradiation. Depending on the dose of ionizing energy applied, irradiation produces minor organoleptic changes. Low dose of radiation has been demonstrated to slow down the ripening of banana. Fourth, disinfestations. Disinfestations is aimed to preventing losses caused by insect in store grains, pulses, flour, cereals, etc. Insect infestation of grains can be controlled by irradiation by low dose of 0.5 to 1 kilogram. 5. Other applications. Reduce or eliminate undesirable or toxic materials including food allergens. Enhance color of meat products resulting in protection of oil from photooxidation and elimination of undesirable color change in oil processing industry.
Now coming to major part of irradiated food is safety of irradiated food. First, radiological safety. Food does not come in contact with radioactive material during food irradiation. Radiation that is too energetic, however, can disrupt the energy balance in the nucleus of food atoms. Second, that is microbiological safety. One of the most important properties of irradiation is inactivation of microorganisms, especially pathogens. It increases the shelf life of product by reducing the microorganism level. Third, toxicological safety. Toxicologically approved by the US Food and Drug Administration, that is FDA. And the fourth, nutritional adequacy. It does not show any effect up to the level of 1 kgY.
Fifth, irradiated foods are not radioactive, does not cause cancer. Sixth, even if it is irradiated 10 times more than approved levels. Seventh, in some cases, irradiated foods are performed over non-irradiated food. 8. Foods can also be packaged and then irradiated.
Regulators of food irradiation involve the followings. Federal government and other scientists reviewed several hundred studies on the effect of the food irradiation before reaching conclusions about the general safety of the treatment. In order to make recommendations specifically about poultry irradiation, US Food and Drug Administration scientists reviewed findings from additional relevant studies. Independent scientific committees in Denmark, Sweden, United Kingdom and Canada also have reaffirmed the safety of food irradiation. In addition, food irradiation has received official international endorsement from the World Health Organization and the International Atomic Energy Agency, that are Food and Drug Administration, US Department of Agriculture, Animal and Plant Health Inspection Service, Food Safety and Inspection Service, Nuclear Regulatory Commission, Occupational Safety and Health Administration, and Department of Transportation.
Let us discuss about the ultrasound.
What is meant by ultrasound? Ultrasound is a form of energy generated by sound waves of frequencies that are too high to be detected by human ear, that is about 20 kHz. Ultrasound has advantages over other traditional analytical techniques because measurements are rapid, non-destructive and precise, fully automated, and might be performed either in a laboratory or online. One of the most widespread and most promising ultrasonic application is the utilization of ultrasound for composition measurement. Power ultrasound is considered to be an emerging and promising technology for food processing in industry. In recent years, the food industry has discovered that ultrasonic waves has a wide variety of application in the processing and evaluation of food products. In combination with heat, it can accelerate the rate of sterilization of foods, thus lessening both the duration and intensity of thermal treatment and the resultant damage. The potential uses for ultrasound in industrial food processing are numerous and are expanding.
Classification. The uses of ultrasound are broadly classified into two groups. Number 1, low energy ultrasound, low power and low intensity. Number 2, high energy ultrasound, high power, high intensity. Low energy ultrasound, this involves the use of frequencies higher than 100 kHz at intensities below 1 watt per centimeter square. It causes no physical or chemical alterations in the properties of a material through which the wave passes and hence non-destructive. They are successfully used for non-invasive monitoring of food processes. Application. Applied in the analytical technique for providing information about the physicochemical properties of foods such as composition, structure and physical state.
High energy ultrasound. This uses intensities higher than 1 watt per centimeter square, typically in the range 10 to 1000 watt centimeter per square at the frequencies between 18 and 100 kHz. Physical, mechanical or chemical effects of ultrasonic waves at this range are capable of altering material properties, that is physical disruption and acceleration of certain chemical reaction. The different application in food involves the following: modification and control of crystallization processes, degassing of liquid foods, enzymes inactivation, enhanced drying, filtration, induction of oxidation reactions to generate emulsions, disrupt cells and disperse exaggerated materials.
Working principle of ultrasound. Ultrasonic wave producing system contains the generator, transducer and the application system. Generator produces electrical or mechanical energy and transducer converts this energy into the sound energy at ultrasonic frequencies. Basically, the transducer are classified into three types, that is fluid-driven, magnetostrictive and piezoelectronic transducers. Fluid-driven. The fluid-driven transducers produces vibration at ultrasonic frequencies by forcing liquid to thin metal blade, which can be used for mixing and homogenization systems. Magnetostrictive. The magnetostrictive transducer is made from a kind of ferromagnetic materials which change dimension upon the application of a magnetic field, and these changes produce sound after mechanical vibrations. The efficiency of system is low somewhat, 60% transfer to acoustic energy. Piezoelectronic transducer. The piezoelectronic transducers produce acoustic energy by changes in size produced by electrical signals in piezoceramic materials such as lead, zirconate, titanate, barium titanate, and lead metaniobate. The piezoelectric transducers are most commonly used devices and are more efficient somewhat, 80% to 95% transfer to acoustic energy.
Effects of ultrasound in a liquid medium. The major effects of ultrasound in a liquid medium are attributed to the cavitation phenomena, which are issued from a physical processes that create, enlarge and implode microbubbles of gases dissolved in the liquid by the compression and decompression of molecules that constitute the medium. Cavitation. Ultrasound is transmitted through any physical medium by waves that compress and stretch the molecular spacing of the medium through which it passes. As the ultrasound crosses the medium, the average distance between the molecules will vary as they oscillate about their mean position. When the negative pressure caused for an ultrasonic wave crossing a liquid is large enough, the distance between the molecules of the liquid exceeds the minimum molecular distance required to hold the liquid inert, and then the liquid breaks down and voids are created. Those voids are the so-called cavitation bubbles. The collapse of the cavitation bubbles creates a transitory hotspot with elevated localized temperature and pressure, which have been estimated to be up to 5000 K and 5000 atmosphere, which can accelerate dramatically the chemical reactivity into the medium. This phenomenon has found numerous applications on the food industry, such as processing, extraction, emulsification, preservation, homogenization, etc.
Parameters affecting ultrasonic cavitation. Frequency. At high sonic frequencies on the order of the megahertz, the production of cavitation bubbles becomes more difficult than at low sonic frequencies. Intensity. The intensity of sonication is proportional to the amplitude of vibration of the ultrasonic source, and as such an increment of the amplitude of vibration will lead to an increase in the intensity of vibration and to an increase in the sonochemical effects. Solvent. The higher the natural cohesive forces acting within a liquid, the more difficult it is to attain cavitation. Both solvent viscosity and surface tension are expected to inhibit cavitation. Temperature. Cavitation is better attained at lower temperatures when the ultrasonic power of the generator is constant. External pressure and bubble gas. If the external pressure is increased, then a greater ultrasonic energy is required to induce cavitation, that is, to break the solvent molecular forces.
Let us discuss about the common ultrasonic devices. The common ultrasonic devices are ultrasonic bath and ultrasonic probe. Ultrasonic bath. The intensity distribution inside a bath is not homogeneous. The aluminium foil test is used in ultrasonic bath. Using a series of aluminium foil sheets, the most intense zones of sonication inside the bath can be quite accurately identified. As consequence of cavitation, the aluminium foils are perforated. The maximum perforation occurs at maximum intensity.
Ultrasonic probe. The ultrasonic converter transforms electrical energy into mechanical vibrations of fixed frequency. The standard and booster horns increase the sonication amplitude. The probes or detachable horns transmit ultrasonic energy into the sample. Detachable horn, which allows the vibration of the booster horn to be transmitted through a further length of metal in such a way that the power delivered is magnified. Power magnification depends on the shape of the probe. The probe gives the highest amplitude magnification.
Conclusion. Ultrasonic processing is establishing itself as a significant food processing technology with the capability for large commercial scale-up and good payback on capital investment. Significant improvements in product quality, process enhancement, and cost reductions are achievable on a commercial scale. The overall application in food processing includes the following: extraction, emulsification or homogenization, crystallization, filtration and screening, separation, viscosity alteration, extrusion, deforming, enzyme and microbial inactivation, fermentation and heat transfer.
Hence, in this module, we discussed about the high pressure processing, in which the different level of high pressure is applied to various microorganisms like virus, bacteria, bacterial spores, and what are the different level of pressure required to inactivate these microorganisms. In food irradiation, we discussed about how irradiation helps to control various foodborne pathogens, and also we discussed about the different applications